17-hydroxysteroid dehydrogenase. 17-hydroxysteroid dehydrogenases 17-HSD, HSD17-BEC1, 51, also 17-ketosteroid reductases 17-KSR, are a group of alcohol oxidoreductases which catalyze the reduction of 17-ketosteroids and the dehydrogenation of 17-hydroxysteroids in steroidogenesis and steroid metabolism. This includes interconversion of DHEA and androstenediol, androstenedione and testosterone, and estrone and estradiol. The major reactions catalyzed by 17-HSD, the conversion of androstenedione to testosterone, are in fact hydrogenation reduction rather than dehydrogenation oxidation reactions. 17-HSD have been known to catalyze the following redox reactions of sex steroids: 20-hydroxyprogesterone, DHEA androstenediol, androstenedione testosterone, dihydrotestosterone 5-ea androstenedione/3-ea androstenediol/3-ea androstenediol, estrone estradiol, 16-hydroxyestrone estriol. Activity distribution. Genes. Genes coding for 17-HSD include HSD17 bone, referred to as estrogenic. Major subtype for activation of estrogens, from weaker forms estrone to estradiol, and 16-hydroxyestrone to estriol. Catalyzes the final step in the biosynthesis of estrogens. Highly selective for estrogens, 100-fold higher affinity for estrones over androstenes. However, also catalyzes the conversion of DHEA into androstenediol. Recently, has been found to inactivate DHT into 3-ea and 3-ea androstenediol. Expressed primarily in the ovaries and placenta but also at lower levels in the breast epithelium. Major isoform of 17-HSD in the granulosa cells of the ovaries. Mutations and associated deficiency have not been reported in humans. Knockout mice show altered ovarian sex steroid production, normal puberty, and severe subfertility due to defective luteinization and ovarian progesterone production. HSD17B2, describable as antiestrogenic and antiandrogenic. Major subtype for inactivation of estrogens and androgens into weaker forms estradiol to estrone, testosterone to androstenedione, and androstenediol to DHEA. Also converts inactive 20-hydroxyprogesterone into active progesterone. Preferential activity on androgens. Expressed widely in the body including in the liver, intestines, lungs, pancreas, kidneys, endometrium, prostate, breast epithelium, placenta, and bone. Said to be responsible for 17-HSD activity in the endometrium and placenta. Mutations and associated congenital deficiency have not been reported in humans. However, local deficiency in expression of HSD17B2 has been associated with endometriosis. HSD17B3, referred to as androgenic. Major subtype in males for activation of androgens, from weaker forms androstenedione to testosterone and DHEA to androstenediol. Also activates estrogens from weaker forms to a lesser extent estrone to estradiol. This is essential for testicular but not ovarian production of testosterone. Not expressed in the ovaries, where another 17-HSD subtype, likely HSD17B5, is expressed instead. Mutations are associated with 17-HSD type Roman III deficiency. Males with this condition have pseudohermaphroditism, while females are normal with normal androgen and estrogen levels. HSD17B4, also known as D-bifunctional protein DBP, involved in fatty acid B oxidation and steroid metabolism, specifically estrone to estradiol, for instance in the uterus. Mutations are associated with DBP deficiency and Perrault syndrome, ovarian dysgenesis, and deafness. HSD17B5, also known as aldo-keto reductase 1C3 aka C3, has 3A-HSD and 20A-HSD activity in addition to 17-HSD activity, expressed in the adrenal cortex, and may act as the androgenic 17-HSD in ovarian thecal cells. Also expressed in the prostate gland, mammary gland, and Leydig cells. HSD17B6 has 3A-HSD activity and catalyzes conversion of the weak androgen, androstenediol, into the powerful androgen dehydrotestosterone in the prostate gland. May be involved in the pathophysiology of PCOS. HSD17B7 is involved in cholesterol metabolism, but is also thought to activate estrogens estrone to estradiol and inactivate androgens dehydrotestosterone to androstenediol. Expressed in the ovaries, breasts, placenta, testes, prostate gland, and liver. HSD17B8 inactivates estradiol, testosterone, and dihydrotestosterone, though can also convert estrone into estradiol. Expressed in the ovaries, testes, liver, pancreas, kidneys, and other tissues. HSD17B9, also known as retinol dehydrogenase 5 RDH5, involved in retinoid metabolism. Mutations are associated with fundus albipunctatus. HSD17B10, also known as 2-methyl-3-hydroxybutyryl-CoA dehydrogenase MHVD. Substrates include steroids, neurosteroids, fatty acids, bile acids, isoleucine, and xenobiotics. Mutations are associated with 17-HSD type X deficiency, also known as HSD10 disease or MHVD deficiency, and mental retardation, X-linked, syndromic 10-MRX-STEN, which are characterized by neurodegeneration and mental retardation, respectively. HSD17B11, HSD17B12, HSD17B13, HSD17B14. At least 7 of the 14 isoforms of 17-HSD are involved in interconversion of 17-ketosteroids and 17-hydroxysteroids. Overview. Clinical significance. Mutations in HSD17B3 are responsible for 17-HSD type Roman III deficiency. Inhibitors of 17-HSD type Roman II are of interest for the potential treatment of osteoporosis. Some inhibitors of 17-HSD type I have been identified, for example esters of cinnamic acid, various flavones e.g. physin.